Welcome to our session on tensor networks for many-body fermionic models. Today, we are going to focus on how we can use tensor networks to solve large interactive quantum many-body fermionic systems. And in particular, we will see how we can understand quantum phase transitions in these very large models. How can we understand the relationship between quantum spin models and quantum fermionic models, and using these techniques to see how we can actually see from calculations spin charge separation in very large Hubbard models. The basic idea of this course is that we have been focusing on two different types of many-body Hamiltonians. We have many-body Hamiltonians that correspond to interacting fermions, where we have a kinetic energy for the free fermions plus some many-body interactions between the fermions. And then we also considered quantum many-body spin Hamiltonians. And up to now, it seemed as if these two types of Hamiltonians were completely different, as if we were dealing with completely different systems. So fermionic Hamiltonians have quantum particles that have fermionic statistics, meaning that the local operators anti-commute, whereas in the case of many-body spin Hamiltonians, the local excitations are bosonic. So spin operators are bosonic operators. So in a way, they seem like completely incompatible systems. So one of the big questions is whether if spin Hamiltonians and fermionic Hamiltonians are actually equivalent, and in particular, if we can map one to the other. And to understand how this may actually happen, it is worth recalling how the local Hilbert space for both fermionic Hamiltonians and spin Hamiltonians looks like. So if we have a fermionic Hamiltonian, we have in practice two different states locally. We have the empty state where we don't have any fermion at all in the site, and then we have the full state, which is the state where we have a single fermion. And since there are anti-commutation relations, we cannot put two fermions on the same site. If you now look at spin Hamiltonians, and in particular at spin 1/2 Hamiltonians, then we also have two different states. We have the state that is down, that is state where our local spin points down, and then we have the state that is up, which is state where our local spin points up. And when we compare these two different local Hilbert spaces, we can actually think that the empty state corresponds to spin down, and the full state of a fermionic model corresponds to spin up. And if you translate this type of relationship to actual operators, you can actually think that the creation operator in the fermionic model corresponds to S plus, whereas the destruction operator in the fermionic model corresponds to S minus. And the way we actually make this correspondence is by realizing that the creation operator brings the empty state to the full state and the S plus operator brings the down state to the up state. So up to this point, it seems as if there's a symmetry between fermionic and spin Hamiltonians, and in particular, as if there's a bijection between the two different Hilbert spaces. But what is important to recall is that actually the operators between different fermionic sites anti-commute for fermions, whereas for spins, they actually commute. And this is actually something that makes this mapping between fermions and spins more challenging. However, this can actually be overcome. And if, in particular, you actually use a more complicated mapping between the spin operators and the fermionic operators, you can actually recover the exact algebra that they should have. So in particular, if you say that the S plus operator corresponds to the creation operator in the fermionic language times a certain operator that we call the string operator, and you take the Hermitian conjugate for S minus, and for S set, you just say that you have the number of electrons minus 1/2, then these types of relationships give rise to mathematically consistent anti-commutation and commutation relations for your spin operators and fermionic operators. And what is important to keep in mind is that this object here is actually an object that if you are in a state that has a certain number of electrons, is just plus or minus 1. That in practice corresponds to how many electrons did you have to flip in order to get to the site that you wanted. And it is usually called a Jordan-Wigner string. And one mathematical way to refer to this transformation is by saying that a spin operator is a fermionic operator times a string, or you can also put the string on this side. What actually is the most important point is that the spin Hilbert space and the fermionic Hilbert space are equivalent times a string operator that you need to put in the middle. And let me emphasize that this string operator is crucial. It is incredibly important to have the string operator in the calculations, but what matters is that from a practical point of view, we can actually map any fermionic Hamiltonian to a spin Hamiltonian if we include this string operator. And this is actually what we do in order to solve quantum many-body fermionic Hamiltonians with tensor networks. Tensor networks, by definition, deal with particles that are bosonic, meaning that the different sides commute, or at least the simplest type of tensor network. And if we want to solve fermionic Hamiltonians, what we do is we first map this fermionic Hamiltonian to the equivalent spin Hamiltonian, including the Jordan-Wigner strings. And once we have this artificial spin Hamiltonian, then we solve the artificial spin Hamiltonian using a matrix product state. So from now on, every time that we refer to the tensor network solution of an interacting fermionic Hamiltonian, we are actually going to refer to this Jordan-Wigner transform Hamiltonian that we solve with tensor networks. But from a practical point of view, we can just think that we have a many-body solver that is capable of dealing with interacting fermionic systems. Okay, so now what we do is start with our interacting fermionic Hamiltonian. We map the interacting fermionic Hamiltonian to an artificial spin Hamiltonian that is unphysical, but it is not a problem for us. And now we solve this artificial spin Hamiltonian with matrix product states, and we obtain the matrix product representation of the pseudo-spin wave function that we could transform back to the fermionic basis using the inverse Jordan-Wigner transformation. And with this, we can use all the machinery that we have for our tensor network solution. And so let us now look at a very specific fermionic model, and in particular, a fermionic model that we already considered using the exact diagonalization, but now we are going to look at much, much bigger system sizes. And we are going to do this, of course, using tensor networks. So the fermionic Hamiltonian consists on a first neighbor hopping. So here we have a term that is just a single particle term, so there are no interactions whatsoever. And then we have an interaction term that it's a density-density interaction between neighboring sites. And in practice, you can think that this model has two different limits. There's the limit where interactions are zero, and in this limit, you effectively have a non-interacting chain that in the thermodynamic limit behaves as a metal. And then you have the strongly interacting limit, which is the limit where V goes to infinity. And in particular, in this limit, your ground state is a charge density wave. So it's a state where you have only charge in this side and no charge in the next one, and charge in this side and no charge in the next one, and so forth. And at some point between V equal to 0 and V equal to infinity, there's a quantum phase transition where you go from a state that does not break translational symmetry to a state that breaks translational symmetry. And the question that we want to answer is how can we see such a phase transition by computing very, very large systems? And so the way we can do this is actually relatively simple. We can just take a system with many, many fermionic sites. These are, here in particular, we are considering a system that has 100 interacting fermionics sites. This is a incredibly large system that would be impossible to solve if we use exact diagonalization, because the many-body Hilbert space would be just too large. And what we can do is, apart from including kinetic energy and many-body interaction, we can actually include a very small term that is a pinning term. And you can think that this pinning term is going to promote that there are a little bit less electrons in the first site and a little bit more electrons in the last side. So in a way, it kind of helps having a charge density wave in the system if the system wanted to have a charge density wave. And what you can actually do is you can look at the ground state of this Hamiltonian in two different limits of the interaction. So perhaps the easiest limit to look at first is the limit of strong interaction, so V equal to 40. If you consider this limit, then this spinning that you put in the Hamiltonian actually helps the charge density wave to form. So it kind of promotes that you have less electrons on one side and more electrons on the other side. And with this help, the whole system enters into the charge density wave state where you have many electrons in one side and much less electrons on the other side. So for V equal to 40, you know that you are in the charge ordered state. You know that you are in the phase that breaks time reversal symmetry because the system, once you added a very teeny tiny perturbation on one of the edges, it just went completely into the charge density wave. If you look at V equal to T, what you actually observe is something completely different. So there are still some oscillations of the charge, and the oscillations of the charge appear because you actually added a small spinning, meaning that you tried to promote that there were less electrons on one corner than on the other. But once you go towards the bulk of the system, the bulk wants to screen this type of oscillation. It wants to make this oscillation as small as possible. And this type of decay of the oscillations is essentially what it's telling you that even in the thermodynamic limit, the system does not want to order. And let me emphasize that the system that we are showing here is a system that is interacting. So it's V equal to T, it's a sizable interaction, but still with this sizable interaction, the system does not want to create a charge density wave, even though you are trying to help it a little bit. It is, of course, something that it's easier to see if you kind of zooming at the beginning of the chain. So you see that for the case of strong interactions, then the charge oscillates very, very strongly and it kind of saturates to a certain oscillation in the bulk, whereas for the case of V equal to T, you have first a relatively sizable oscillation that then it decays as you go towards the bulk because the bulk does not want to have an oscillation in the charge density wave. And this is something that you can do systematically for every single interaction. So here, what I'm plotting is effectively that charge in each side as a function of the external interaction and including the pinning field. So the pinning field essentially creates a little bit less density on one side than in the other. But what you observe is that when you are at zero interaction or finite interaction, then the bulk decides to not have this oscillation at all. So it becomes completely green. That corresponds to a density 0.5. But then eventually, once you go to a certain critical value of V that is actually 2 in the thermodynamic limit, then the system as a whole decides to have a charge density wave. The pinning the edges helps, but the bulk itself wants to go completely into this charge ordered state. And this is what we call a quantum phase transition. The system goes from state that breaks translational symmetry to a state that does not break translational symmetry. And this happens at zero temperature, and it happens at the critical value of the many-body interaction. Let us now look at some other way of observing phase transition, which is by using fermionic correlation functions. The idea is relatively simple. From a perturbation theory point of view, you can think that this notion of putting a certain pinning field and measuring the density in the other sides can be rephrased in terms of a Kubo formula. And actually, you can think that this type of measurement or this type of perturbation and measurement corresponds to finding the non-local fermionic correlator, so the non-local particle-particle correlator. And in particular, if you have a system that is a metal, this non-local particle-particle correlator is long-ranged. And if it is long-range, it actually decays using a power law. This is very similar to the phenomenology that we observed and that we discussed in quantum magnets. So we had a quantum magnet that was gapless, then the spin-spin correlator decayed as a power law. Whereas if you have an insulator, then this particle-particle correlator decays exponentially. And the parameter of this exponential is what we call the correlation length. And it effectively tells you how long range the correlations in the system are. And so we can use this type of quantity to actually characterize the phase transition in the interacting fermionic model that we discussed before. So the interacting fermionic model actually has, again, our two terms. So it has the kinetic energy and it has the interaction term. And what we can actually think is that the two phases of this interacting fermionic model are completely different in terms of their correlation lengths. So the metallic phase, which is the phase where V is equal to 0, is a metal, of course, and it has long-range correlations because it is metallic and it has excitations at arbitrarily small energies. What this actually means is that correlations are going to decay as a power law. Whereas in the charge density wave state, correlations are going to decay exponentially. And the reason is because the charge density wave state is actually an insulator, namely that you need to pay a finite energy in order to create an excitation. And the fact that you need to pay a finite energy effectively makes all the correlations to decay exponentially. And this is something that you can directly see by computing the non-local correlator of this model. So in the non-interacting case, what you observe is that the non-local correlator between the first site and the end site, let's say, it starts oscillating and decays, but it decays relatively slowly. And this decay is a power law decay. Whereas if you start ramping up the interaction, you see that as you ramp up the interaction a little bit, then the decay continues being power law, but it's perhaps a little bit faster. And when you take a very large interaction, and in particular an interaction that it's in the charge ordered state, what you actually see is that the decay is very, very fast and it very quickly becomes 0. And if you actually do a log-log plot, you can very easily see that both for v equal to 0, that it's the non-interacting case, and v equal to 1, then your decay is very, very slow. This is your power law decay. Whereas for v equal to 6, which is the exponential decay, you see a perfect line in the distance versus log of the correlator. All right, so now we are going to look at a different type of correlator. This is no longer a particle-particle correlator, but it's a 4-point correlator. And this 4-point correlator is a correlator between destroying an electron inside J plus 1, destroying an electron inside J, creating it in I plus 1, and creating it in I. So in a way, it actually tries to see how much the system wants to destroy 2 electrons on one place of the system and create 2 electrons in some other place of the system. So in a way, this is measuring how susceptible the system is to create pairs of electrons or Cooper pairs. And so we can start by looking at what happens if we have no interactions, repulsive interactions, or attractive interactions. If we have no interactions, then this correlator decays at a certain rate, and you see in the log plot that it decays at this rate. If you increase interactions, and in particular use repulsive interactions, what you observe is that the correlator decays as well, but now it decays faster. What this actually means is that repulsive interactions quench this type of double electron interaction. So repulsive interactions do not want to create these types of Cooper pairs. Whereas if you add attractive interactions, what you actually see is that decay is slower, and having this slower decay actually means that the system is more likely to want having these types of double electron interactions. And in a way, this is a signature that attractive interactions would promote Cooper pairs in the system. Let us now look at a slightly more complex model. This is the so-called Hubbard model, which in practice is also a model for fermions, but now fermions have spin degree of freedom. And for this model, we are going to consider that there's a first neighbor hopping, that is the kinetic energy. And then we have some many-body interaction that now it's a density-density interaction. It's an interaction between density up in one side and density down in the same side. And what is important about this model is that it has something called spin charge separation. And what this actually means is that the dynamics of the charge is different from the dynamics of the spin. And let me emphasize that the model originally has electrons, and the electrons themselves have both charge and spin. And this charge and spin cannot be separated between individual electrons. But now when you consider a many-body system that has many, many electrons, these many-body interactions effectively allow you to split into the electron, to put the charge on one side and the spin on the other side. And the intuitive way of understanding this is by recalling that if you have a Hubbard model at half filling, at strong interactions, so at strong U, the system is a gapped electric insulator, is a Mott insulator. Whereas in that very same regime, you can actually map the Hubbard model to the Heisenberg model. And the Heisenberg model is actually a gapless quantum magnet. It has spin 1 excitations, which is what we call spin-ons. So at strong U, two things happen at the same time. First, charge is gapped, so you need to pay a finite amount of energy to create a charge's excitation, and spin is gapless. So you can pay an arbitrarily small amount of energy to create a spin excitation. So the practical question for us is how can we observe this spin charge separation using tensor networks, and in particular computing different expectation values. So let us start with the charge gap. So observing the charge gap is actually very easy. You just have to take your original Hubbard model and compute the non-local particle-particle correlator. So you actually compute the correlator between the first site and the site number n. And what you observe is that at, let's say, no interaction, you have an oscillation of your non-local correlator, an oscillation that decays as a power law. And when you increase the interaction, you see that the oscillation decays faster. And in particular, the stronger the interaction, the stronger the decay. And the decay, of course, becomes exponentially fast. And this is, of course, something that you can very easily see if you plot the logarithm of the absolute value of the correlator. So you see that in the non-interacting case, the correlator almost doesn't decay. Because actually just as a power law. And as you increase the value of the interaction, then the correlator decays faster. In particular, it decays exponentially fast. You can now look at a different type of correlator, which is the spin-spin correlator of the Hubbard model. So this spin-spin correlator is just a fermionic correlator where you replace this spin operator by the representation in terms of fermionic operator. So this operator is in practice Pauli matrix times creation operator of the fermionic side and annihilation operator. So in practice, the non-local spin-spin operator is a biquadratic non-local expectation value. And what you actually observe is that the opposite behavior emerges. You start with the non-interacting limit where u is equal to 0, and you see that your spin-spin correlator decays, and it decays relatively quickly. And then as you increase the interaction, you see that the correlator becomes more and more long-ranged. And this is something that you can systematically observe if you plot the logarithm of the non-local correlator. And what you actually observe is that whereas at u equal to 0, the spin-spin correlator decays very quickly, as you switch on the interaction, then the correlator decays much slower. And in particular, it seems as if the stronger the interaction, the more long range your correlator is. And of course, this has an upper bound. You can actually look at a different type of correlator. This is also a biquadratic correlator, but this biquadratic correlator is actually a correlator that tells you what is the tendency of the system to form Cooper pairs, very similar to what we showed before in a spinless fermionic system. In particular, we are going to use this correlator, so we are going to destroy an electron down inside J, destroy an electron up inside J, and then create one electron down inside I and create another electron up inside I. And what you observe in this case is that taking as a reference the non-interacting case, if you take repulsive interactions, then your system does not want to have this type of non-local pairing correlation, whereas if you take attractive interactions, then the system actually likes this type of non-local, let's say, pairing correlations. And once again, this in a way is telling you that attractive interactions kind of promote having this pairing of electrons, whereas repulsive interactions do not promote having this pairing of electrons. So from the previous calculations, we learned three different things. First, that electronic repulsion creates a gap in the electronic excitations, and at the same time, it makes your spin excitations gapless. This gives rise to what we described as spin charge separation. And then at the same time, repulsive interactions quench these pairing correlations, whereas attractive interactions enhance the pairing correlations. So far, we have been focusing all the time on correlated fermionic system. We have not asked ourselves if the fermionic correlated system could actually be described with mean field theory. We just assumed that it cannot be described, and we used the full many-body solution using tensor networks. But it is worth asking ourselves whether, if it's some regime, a correlated state can be actually described accurately using mean field theory. And the way to characterize this is by the so-called correlation entropy. And the idea is very simple. Let us think about the Hamiltonian for spinless fermionic chain. We had kinetic energy and we had many-body interaction. And this system had two very different limits. It had the non-interacting limit that whose ground state is a metal, and of course, as it is non-interacting and it is a metal, it has a mean field description, and then it has the strongly interacting limit that we said it was a charge density wave, and we call it strongly interacting, but actually this type of ground state can be exactly written down as a single particle state, right? This is a state where we have one electron in this side and no electron in this other side, and you can write this down exactly as a product state. So technically speaking, one can describe the V equal to 0 limit using mean field theory, and one can describe the V equal to infinity limit also using mean field theory. Intermediate values of V are cannot be described using mean field theory, but these two limits can be described. So an important question is how can we know when we can use mean field theory and when we cannot? In the case V equal to infinity, clearly we can use mean field theory, but how do we know that in some intermediate case we can or we cannot? And for this, we can use a relatively simple object, that is the correlation entropy, and it comes automatically from the non-local particle-particle correlators that we described before. So you can think that you could actually compute all the non-local correlators. So C dagger I, Cj, and form a matrix that you call the correlation matrix, that it's chi ij. As a matrix, it can be diagonalized. And when you diagonalize a matrix, you get a certain set of eigenvalues and eigenvectors. And in particular, if your wave function is a Slater determinant, if your wave function is a fermionic product state, then the eigenvalues of this matrix are all 0 and 1. And this is very easy to see just by writing down this correlator in the diagonal basis. So in the diagonal basis, you can think that this would be psi dagger k psi k, and in that basis, the matrix is diagonal and it has values 1 for the single particle wave functions that are occupied and 0 for the single particle wave functions that are unoccupied, and therefore all your eigenvalues are 0 and 1. And once you have something whose eigenvalues are 0 and 1, you can try to define a quantity that tells you how much you depart from that condition, that it's an entropy. So you can take this matrix, compute the eigenvalues, and compute the entropy associated to those eigenvalues with the usual definition of an entropy. And when you compute this object, you can effectively know if your original wave function was a Slater determinant of product states. In practice, if the entropy is 0, then it was. And if the entropy is non-zero, then your many-body ground state is not a product state, but it's something else. So in a way, this entropy allows you to know if you have a product state, or if you have some state that can be described using mean field theory, or if you have something that cannot be described using mean field theory. And so let's use this idea with the interacting spinless fermionic chain. We're going to take the correlation entropy of the system, and again, the correlation entropy is computed as you take the ground state, you compute all the correlators of the ground state that forms a matrix, you diagonalize the matrix, and with the eigenvalues, you compute the entropy. And then we are going to plot this as a function of the many-body interaction. So for interaction equal to 0, we know that our ground state is a Slater determinant, is a product state, and therefore the entropy is 0. For the case of very large interaction, we also know that the ground state is a product state because it's this state that has one electron here and no electron there. And of course, this can be written in a mean field fashion. And then in the middle, you see that the correlation entropy peaks. So what this is actually telling you is that the ground state of this system is strongly correlated around v equal to 2. And by strongly correlated, we refer to wave functions that cannot be described with mean field theory. Whereas when you are in the limit where v is very, very large, you can actually describe this using mean field theory. And so this type of object systematically allows you to characterize when your ground state is actually strongly correlated and when you can describe the ground state using mean field theory. And this is, of course, something that can be applied systematically to any fermionic Hamiltonian that you have. And in particular, you can even apply this to the Hubbard model. So you can take a Hubbard model that you modify in order to drive it to the mean field solution. So we are going to take the Hubbard model that has kinetic energy over here, many body interactions, so the Hubbard interaction, and then an extra term that is mean field antiferromagnetism. This is the term that you would have gotten if you solve the Hubbard model using mean field theory. And in a way, by switching on and off this term, you can drive your ground state towards a mean field ground state, or you can keep it in the strongly correlated and entangled state. And so you can actually see very easily what this type of term does to your Hamiltonian. This is effectively an alternating exchange field in the sides. And you can see that for Jz equal to 0, you effectively have a system that does not break the universal symmetry, that it's a quantum magnet. The magnetization is 0 everywhere. This is like the ground state of a one-dimensional Heisenberg model. This is a spin liquid state, if you wish. And then as you increase the value of Jz, you are essentially increasing this Stocker exchange field and are creating a local magnetization on each side. And you can think that when you are over here at large Jz, you are actually promoting the ground state of the mean field Hamiltonian. And this is something that you can systematically see by looking at the correlation entropy of the ground state as a function of Jz. If Jz is equal to 0, you are in this strongly correlated and entangled state that has a very large correlation entropy. And as you increase JZ, then you start driving more and more and more your system towards the mean field solution, which is this solution that has a Stocker magnetization and that breaks time reversal symmetry. This is everything that we were going to discuss about physical systems that use interacting fermions. And in the last part of the recording, let us just briefly discuss about the different tensor network algorithms, and in particular, how we can actually minimize a matrix product state, which is a task that is, of course, incredibly important for everything that we've discussed so far, but that we somehow didn't explain in detail yet. So, as you recall, the idea of matrix product states is that we wrote a wave function using a tensor, and in particular using a product of local matrices. And for tensor networks and matrix product state, it is usually very useful to have this type of schematic. So we denote scalars as a single point or a single circle, vectors as a point that has one leg, matrices as a point that has two legs, and then generalizations of matrices that we call rank 3 tensors as points that have three legs. So for example, if we make a product of a matrix times a vector, we are essentially putting this leg together with this one and ending up with something that has a single leg. And of course, matrix times vector gives rise to another vector. So this graphical representation is a very convenient way of writing all these algebraic operations. And so for us, a matrix product state can be represented in this form. So we have a product of matrices. So in practice, what we have is a set of nodes, and each one of these nodes is one of these matrices. The product of matrices is denoted as this line that connects one matrix with the other. And then this subindex, that is the spin superindex that denotes the physical spin, is effectively this leg that is free. So these indexes are the physical spins or the pseudo spins if you did a Jordan-Wigner transformation for a fermionic model. And these other indexes are just internal indexes that they do not have necessarily a physical meaning, but they are just part of the indexes that you need in order to make this product. Those were the wave functions. Those were the matrix product states. But if we are dealing with Hamiltonians, we also need to represent matrices, and matrices understood as operators of the many-body Hilbert space. And the operators of the many-body Hilbert space are represented in a very analogous way by using so-called matrix product operators. So instead of having a set of nodes that have two or three legs, we now have nodes that have three or four legs. And we have two sets of legs that correspond to the two pre-indexes of the operator. So you can think that these are the rows of your operator and these are the columns of your operator. And these legs over here are the internal indexes that essentially allow you to write down this operator in a very big Hilbert space in a reduced form by using products of local tensors. So this is just the matrix generalization of a wave function using matrix product states. And now one of the most important operations for us is to do Hamiltonian times wave function. And of course, the Hamiltonian is an operator. So the basic idea is that when we do Hamiltonian times wave function, what we have to do is to contract the legs of the operator with the free legs of the matrix product state. And when we do this operation, we end up with another object that has these free legs over here that, of course, corresponds to a new matrix product state. And the whole idea of matrix product states and matrix operators, and in particular the algebra, is that when we do this operation, we can actually contract this tensor and obtain a reduced representation of this tensor by doing a set of singular value decompositions in every single link. And so the most important operation for us is to actually find the ground state of the system. And the way to find the ground state is actually relatively simple, and it simply uses the variational principle. You can now think that this matrix product state that you're using here is just a variational function, and as a variational function, you can try to minimize it. And when you minimize this variational function, you essentially end up with the ground state. So the idea is the following. So you define this functional. So this is the expectation value of the, let's say, variational wave function, Hamiltonian variational wave function, normalized to the norm of the variational wave function. For convenience, you can rewrite this using a Lagrange multiplier. So your objective is in practice to minimize this function over here, which is the expectation value of the Hamiltonian minus the norm of the wave function. And from a variational point of view, you can think that the only thing that you need to do is to compute first the functional derivative of the energy with respect to every single matrix that your matrix product state has. And when you obtain a matrix product state that fulfills this condition, then you know that you are in a local minima. And once you use this tensor representation and diagrammatic representation of your tensor network, you very quickly realize that this condition of derivative of the energy with respect to the matrix product state matrix simply can be written simply as this form of diagram. So since the contraction of the network is just a product of tensors, doing the derivative with respect to one of the tensors just leaves all the other tensors that you did not consider. And so what you do in practice is you solve this for this tensor. And in practice, this involves just doing a singular value decomposition and diagonalization. Then you do the derivative with respect to the next tensor and with respect to the next one, and you do this many, many times. So you first sweep to the right, then you sweep to the left, then you sweep to the right, and you do it as many times as you need. And once you have converged to a matrix product state in which, let's say, more sweeps do not make any change, then you know that you effectively ended up with the lowest matrix product state from these types of local updates of the tensors. And this algorithm is effectively equivalent to the density matrix normalization group. One last point that is important to consider is that in these lectures, we have been focusing on matrix product states, which are the simplest architecture for variational wave functions that you can use that you can write down with tensor networks. There are, of course, many other different types of architectures, and you can think about a two-dimensional extension of a matrix product state, which is a PEPS, that is, of course, very important for two-dimensional quantum systems or even more irregular types of networks. And you can think that all these different architectures allow you to parameterize a different set of matrix product states. From the point of view of the entanglement properties, each different architecture has completely different entanglement properties. And actually, projected entangled paired states allow you to parameterize a set of wave functions that has more entanglement than matrix product state. It has the disadvantage that they are also harder to optimize. And of course, if you think about other architectures, such as multi-scale entanglement minimization group, then those allow you even to have bigger and more different types of quantum entanglement. So in practice, you can think that tensor networks are a whole family of variational algorithms, a whole family of variational algorithms that in a way allow you to parameterize quantum many wave functions